Hey everybody, it's Ribley back again. Hope you guys are doing well. So we're done, believe it or not. We got two little sections left to do, but we're pretty much finished out of the book as far as being able to do what we need to do to be prepared for both the AP and the CBE. So, all right, I want to expand just a little bit on what we talked about with the Taylor polynomial, okay? The thing that we got to understand here is that f of x is going to equal, it's going to be exactly equal to the Taylor polynomial. Remember, this guy is, in theory, the nth degree Taylor polynomial, plus the error. Now, if you remember in the past, we've referred to this as Rn of x. So, for example, if I want to do f of x equals e to the x, which I know is also equal to the sum as n goes from 0 to infinity of x to the n over n factorial. Okay, and I want this to be approximated by, let's go t. I want e to the x. I want e to the x to be approximated by, what do we want? Let's go t sub 5 of x, which is the 5th degree Taylor polynomial. Okay, so that's easy. Really, all I got to do is build this guy out, right? So when n equals 0, this is 1 plus. When n equals 1, right, I get x over 1 factorial, which is 1, plus x squared over 2 factorial, which is 2, plus x cubed over 3 factorial, which is 6, plus x to the 4th over 4 factorial, which is 24, plus x to the 5th over 5 factorial, which is 120. All right. However, remember, this goes to infinity. This goes forever. So what remains is r sub 5 of x. Now, we could write that if we had to, right? That would just be the sum as n went from what? From 5 to infinity, or excuse me, from as n went from 6 to infinity, right? This thing could be represented as the sum as n goes from 6 to infinity of x to the n over n factorial. Now, we know that that e to the x and its Taylor series, which is really a Taylor polynomial, they are only equal to each other if r sub n, we know that if r sub n goes to 0 as n goes to infinity, right, then I know that these two, I can claim that this is equal to this, right? Because as n goes to infinity, theoretically, r sub n should go to 0, and you end up with the Taylor polynomial equaling f of x. On the radius of convergence. You always, when you're dealing with power series, you always have to be thinking, what is my radius of convergence? Well, the cool thing about this is my radius of convergence is all reals. That's a negative infinity to infinity. That works everywhere. Pick any point on e to the x, and it can be approximated by this guy. Okay, now watch this. I'm going to say, I want to know what e to the 4th is. Okay? And I'm going to say that e to the 4th is approximately equal to this guy, right? It's just a Taylor polynomial at 4, which is just going to be 1 plus 4 plus 16 halves plus, what do I got? 60. Ooh, this is going to get ugly, isn't it? 64 sixths plus 256. Good gracious. Where are we? 24s plus 1,024 1/20ths. And then I could add this up. But the question that I want to know is, I know that e to the 4th is going to be exactly equal to this guy plus the error, the remainder. That's why they use an r, right? R sub 5 of 4. In other words, all those extra terms, that 4 to the 6th, 4 to the 7th, 4 to the 8th, etc., divided by 6 factorial, 7 factorial, 8 factorial, etc., if I were to just plug it in. So the question becomes, how big is this? How big is this? How far off am I? Because once I plug this in my calculator, which I'll do here in just a sec, once I plug it in my calculator, how sure am I that I can use this as a reasonable approximation? The way in which we do that is we do it with what's called the Lagrange error bound. Now remember, hitherto for alternating series tests, remember, that was just this guy, b sub n times -1 to the n, right? And it doesn't matter where we start here. We knew this. We knew that absolute r sub n was always excuse me, was always less than or equal to b sub n plus 1, as long as it was alternating series and it converged. Remember, if they don't converge, we're not having this discussion. It's kind of like, if you can't talk sense, I'm not going to talk to you at all. And then we only talk sense if we're talking about convergent series. All right? The problem is I mean, look at e to the x. It's not alternating series. It's a standard issue power series. What we need is an end-all, be-all for power series that aren't necessarily alternating. Okay? And that is the Lagrange error bound. So that's just a little introduction to it. So here's the Lagrange. Let's go Lagrange error bound. Here's how it works. Now, we've seen this before. Remember way back when we were doing numerical approximations? Remember, everybody's like, wait, why do we need this? This is crazy. Well, just bear with me here just a sec, okay? All right, here's how this works. I am going to write, I know the absolute r sub n of x, right? That's how you always write it. That just means the error is less than or equal to m. This is a big ol' M. Now, don't panic. You'll see what we're doing here. If I go n times, or excuse me, m divided by m plus 1 factorial times x minus a, the absolute value of that raised to the n plus 1. Okay? Now, think about this for just a sec. Let's just look at this. Before I do anything, I really need to define this guy, don't I? Remember back when we were doing the error bounds for trapezoidal and Simpson and midpoint approximations, we had that k. Remember that guy? And k had to be greater than or equal to the absolute value of, it was like f double primed of x on ab, right? Remember that guy? And it was the fourth derivative if we were talking about the Simpsons approximation. Well, we're going to define m similarly. M is defined as, m is going to be greater than or equal to the absolute value of the n plus first derivative of x on, now think about this, this is going to be x minus a, absolute x minus a less than d. All right, so